Still a few more people coming in, but I think we are getting started. So the topic will be choosing the right machine learning and AI sensors for condition monitoring applications. My name is Pasi Myllymäki. I'm from STMicroelectronics, and I have been working in ST for 15 years, focusing especially on sensors and then condition monitoring. And I'm actually Finnish, by the way, originally. And surprisingly, that will be the exact agenda then for the speech, that we will have a quick introduction to condition monitoring in general. Then we go through some of the key components just to explain where they can be used and basically which is the optimized sensor for which purpose. Then I will show you some details on this new STWin.box development tool, and then we'll have some examples from practical real-life testing and summary in the end. All right, let's get started. So condition monitoring overview. So what you can see from here is that, for example, to monitor an industrial motor, so the first step is to attach sensors and start collecting data. Then, based on this, we can set different kind of parameters and set different kind of, monitor different kind of trends and set different kind of threshold levels and make alarms based on this. Now lately, when we are getting more and more processing power in the main hosts, this kind of local processing and connectivity, for example, the cloud, is very easy nowadays. And this is, in a way, helping to boom up this type of application. And then the next steps is really to do more and more data analysis and then different kind of machine learning. And from this, we can then go from condition monitoring to real predictive maintenance. And on this slide, I will show you some more concrete examples, what kind of sensors you could use. So this is actually coming from different kind of theory books of predictive maintenance. And for example, for a motor, when the conditions start to change over time, one of the first artifacts that these start to generate is ultrasound. Something that you could measure with microphone that we will then come back in the coming up slides. The second artifact is vibration. So this happens very early that the machines start to vibrate. Then power, measuring power and current would be the next step. Then, for example, measuring magnetic field on top of the motor. Then in some applications, for example, anything related to air, it's better to measure the air pressure instead. Then at some point, these devices really start to make noise, and also their temperature starts to go up. And then eventually, you end up in smoke and failure, what you for sure want to avoid. So the first step would be, as said, to mount this kind of sensor on top of a motor and a pump. And then nowadays, we can actually run even sophisticated algorithms, anomaly detection within the sensor itself. This way to have very low power systems. The other option is to have a dedicated microcontroller for this and run more complex algorithms and really identify what could be the reasoning for this failure in this specific device. And then, of course, when running all of this in the edge, this will help you to make it in very low power. And then you can time to time send the information to cloud where you can do more and more analysis. All right, but let's now start to have a look on the exact components. And I will start from the microphone. So you will, by the way, get the presentation. So I will just mention some of the key parameters here. But this microphone, the part number is visible in here. This can go up to 80 kilohertz of frequencies and measure this kind of ultrasound. And one of the key merit is this signal to noise ratio on this component. And you can see actually the applications here that different kind of motors, especially if you have gearboxes, bearings, these start to generate the artifacts in ultrasound. But then also anything related to gases, so pneumatic system. If you have a gas leakage, this will produce ultrasound. And then actually the last one in here, anything related to electricity and electricity shocks and pulses. So creating spikes, that's what creates also ultrasound. The next example from the graph also was the vibration. And here we have very dedicated and actually brand new component. This is roughly 2 years old acceleration sensor measuring vibration, so we call it vibration sensor. And the key merit of this one is that it goes up to 6.3 kilohertz of bandwidth. So from this perspective, it's perfect to monitor pumps, motors, and basically anything with rotating machines. You can see the other key parameter here, the noise density. So this is so accurate that you can start to see if you have a defecting bearing in your system. That starts to create very small impulses, vibration, and you can measure it with this component. Moving to the next component example. This is a 6-axis IMU component. So what it has is also the accelerometer component, so doing the vibration measurement, but then anything related to rotation. So if the object is rotating like this, you will need a gyroscope for this purpose. And then also, if the object is rotating like this, you will get more information from gyroscope specifically. And actually the key applications for this component could be then related to robotics. These are moving quite freely. Then windmills or wind turbines. So again, they are rotating, and actually we are using this component to measure how the blades are vibrating and what is the speed of the wind turbine. The key parameter from the component perspective is this bias instability. So it means that the component drifts only 3 degrees per hour. So it's very accurate component. Also, the other key parameter is the noise density. So again, to measure something very weak signals, you need very low noise in general. And one of the applications could be also this kind of forklift type of applications to measure how the forklift is vibrating and how people are using it when they're operating it. One more component example on vibration specifically, and this is actually an inclinometer, so it's measuring accurately tilt, so angle. But what you can see from the component is that it's optimized up to 260 hertz of bandwidth, so very low frequency vibrations in this case. So the examples could be now related to the 5G antennas to see if they have been tilted because of the wind or storm, or then again windmills, wind turbines, but in this case the pole itself, how the pole is vibrating. Again, you can see the key parameters, noise density, which is actually a bit smaller than the previous components. But in short, to summarize that the message is that we have plenty different kind of sensors, and they are all optimized for different type of purpose, and in a way, to make benefit of the AI, you need to have the right kind of sensor to measure the right things. And as I mentioned, this inclinometer was for very small frequencies. This 6-axis component went up to 2-3 kilohertz, and then this guy went up to 6 kilohertz for the motors and pumps. And then with the microphones, you could go up to 80 kilohertz. Just a couple other examples that we also make magnetic field sensors. The exact part number is here, but the idea is that when the motors are rotating, they are generating magnetic fields, and actually in some cases to catch some of the failures, it makes sense to measure this instead, or as an additional sensor. And in this case, you would again mount it on top of a motor or a pump, for example. But then, if it's somehow related to airflow, in this case it makes sense to use pressure sensors specifically. So this component would be then perfect match for different kind of HVAC systems, and basically anything with air filters that you can start to see when the filter is getting clogged. This is one type of condition monitoring of machines, and you can either use 1 or 2 sensors of these to make this type of measurements. Just as a background, this type of components are also being used, for example, in vacuum cleaners to see when the bag is getting full. And then one example of a very commonly or basically maybe even the most important parameter to measure is temperature. And even this is a brand new sensor. And the new thing here is that it measures the temperature from this pad in here. So again, it simplifies to make the total product when you just guide the heat into this pad, and you can make the temperature measurement with very low latency, and this way catch again the failure. So this would be the exact model proposed for this type of use case then. All right, so that give you the introduction of different kind of sensors we have for different kind of use case, and then the next section will then describe how you could try them out easily. And we just announced Q2 this year, this STWin.box development tool. It comes in this type of blister that you see in here. But basically when you put it together, you have everything from the hardware with the battery included, and you can start using it right away. Here you have the exact list of the sensors, what you have inside. And it's actually including all of those that I mentioned in the previous speeches. So from that perspective, it works with many different kind of applications. We can start from here, the acceleration sensors. So to mention that we had the 6 kilohertz component. This was the 6-axis IMU, but we have also one which is a very low power component. So this could be used, for example, for the initial wake up of the failure, that this component takes only 0.4 microamps of current, and then it could wake up the whole system based on a small shock on your device. And it's actually being used very commonly together with this other guy, which takes more current when it's making the measurements. Also, we had here the inclinometer component for the accurate angle measurements. And then we had the magnetometer, 2 microphones in here, barometer, and the temperature sensor. But actually, to make the vibration measurements accurately, even in this box, we can measure them roughly up to 1 kilohertz. Then you start to have different kind of resonances within this box itself. So there's the battery inside, and in a way this is optimized to be a low-cost tool for the initial development. But in this case, we are also offering this kind of external flex cable and this kind of small board that you would then attach to your device directly, even glue it. And this is indeed needed if you want to go up to 5-6 kilohertz of bandwidth. And then this should be also taken into account in the final end product design, that to make it very robust, avoid any resonances, and then in some cases some have even remade this board and plastics from aluminium, for example. So make it very accurate to capture the data logs also very accurately in the very beginning. Another new thing on this development kit is for the microphones and pressure sensor, that we included this kind of protective acoustic vents. These are coming from company Gore, so a bit similar to what you used in the different kind of fabrics. But what we did is that we measured this up to 80 kilohertz now and verified that it works up to ultrasound. So again, something that you would need to take into account in the final end product design to ensure that the dust and water is not entering all the way into your end product. And this type of Gore membrane would fit very well then for the microphone use cases. All right. So the next topic is then that how to easily use this type of board. And the easiest way is to use the STBLE sensor app. So you just connect with your phone into this device, and what you can actually do is to set up all the parameters for the different components. First of all, enable them, but for example, set the sampling speed for each sensor. And this next slide is a bit complex, but just to highlight that you can actually do the configuration either from the phone using a BLE connection to the board, or then you can do it with the USB cable from the PC. So this might be easier in some cases. And then you can log the data into a SD card that we have in here, or then log it through USB directly to a PC. Again, this is a bit complex slide, but just to highlight that we are using specifically Python in our development tools. So when you get this software package from our pages, you will get all the pre-made tools to use Python specifically to make data logging. And for example, with these arrows, we are highlighting some of the scripts that we have made. So first of all, to make different kind of data format conversion. If you are locking the microphone, you can then generate WAV file on this and even hear it with your own ears. Or then, first of all, to visualize the data, that to make different kind of plots. And this is very, in a way, good in the very beginning, this way to identify what kind of peaks you would have, for example, in the data. And this is now showing the exact GUI from this Datalog2 software package that we offer. And you can see that we can enable all the sensors again here, and then click the Start Log button and start making the measurements. But let me move to the next section of practical examples that we have then done. And if you would like to run this yourself, the steps are just put in SD card, use this Datalog2 software package, open the BLE sensor app, and then eventually this is what you get in the SD card, that these different folders with the different data logs. And then in the next we will have a video showing when we are doing this type of motor monitoring. So this is an electric motor connected to a load, and then we put the STWin box in here. And hopefully the video will then play without issues. So yes, it's blinking here, and then you can see in bigger scale the screen in here. And first we just connect to a device, so it's visible here. And again, you can see all of these different sensors that we have here. We are now using this high bandwidth 6 kilohertz sensor, which is configured up to 2G of vibrations. And this is roughly what we normally see in motors specifically, that it's not that much higher vibrations. And now we just click the start button to make the logs. We put on the motor to spin at the same time. And then this is actually what you would get out from the Python scripts. So exactly these kind of graphs. And shortly we are adjusting then the speed of this motor in here. You can see that it starts to run with slower beats, and then you start to see in here basically the vibration level is getting lower. So we are highlighting this because it's in normal applications it's very difficult to know what kind of vibrations you might expect. So really making this kind of test in the very beginning is the easiest way to get started. All right. Then we have the other example to run the Python environment on a PC directly. That you can again see the GUI that I was mentioning earlier. In this case, you don't even need the SD card inside. And again, all the data logs are then inside those folders after these data logs. And in this case, you just open the data log GUI. This is a Python script. And before this, you just need to install the Python environment, but that's the only thing you need. And then we just connect to the board. And after this, again, we have all the sensors now enabled here. So it's very easy to make data logs from all the sensors. You actually create quite a lot of data using this. And again, we have connected this to the same motor that we have in our motor lab. And yes, you can see in here the vibrations the motor is generating. And by the way, with our sensor, we are measuring all the 3 axes, and in this case, the top one here, it also has the gravitational force. So that's the reason why it's situated in this 1G level of values what we get out. But this can also then easily be filtered out. And again, when we were putting the motor to run slower, you can see that the vibrations went down, and also now when we stopped, it completely stopped. Usually the Z-axis is the most strongest one, because it's pointing towards the load in this case. All right, so based on those measurements that we did in the lab, just to show one more bit more practical example, that this is actually from apartment building, 23 kilowatt heat pump, and the same principle is here. Now we just even mount it on the outside chassis of this type of equipment, and you can see in here again in Z-axis, especially when the compressor is starting in this type of equipment, that will start to create vibrations, and then over the time this can start to change. All right, so that was the part how to make the data logs, and actually the reason why we emphasize that so much is that if you want to create AI algorithms, the first step is to collect data, and for this we have available this type of Nano Edge AI Studio, which is simplifying this work. And as you can see from here, the very first step is the data acquisition in here. So just in the big picture, that compared to traditional programming, where you set each of your commands, basically what you want to do, in the AI type of algorithms, you always just collect the data, and then based on the data analysis, create the algorithm for you. And this tool, then Nano Edge AI, it helps you to do different kind of data processing. Then it will select you the best matching model for your exact use case based on the data that you have collected. And then you can test this within the tool itself, and then create a library in this last step in here, and then to insert that AI algorithm into your STM32 microcontroller, or then to the ISPU component, which is a sensor having a dedicated core to run these type of algorithms. Just one picture of the tool itself, that it supports this STWin.box by default to make the data logs, but then all those steps that we showed earlier using this Datalog2 software, it can also read those indirectly. And personally, I would say that using this Datalog2 and Python, if you're just familiar with that software, it's a very powerful tool to make data analysis specifically, and to make the first plots to understand a bit what kind of things you are seeing in the data. But then the benefit of this Nano Edge AI specifically is that it will also help you to visualize the data. And then in here, it's a bit small text, but based on the iterations that it runs on the data, it will then give you the percentage number that how well it could detect different kind of anomalies, for example, in the data. Now in this case, the number is roughly 97% in this one. And the exact perfect use case for this could be, for example, fan monitoring that you see in here in the picture. That the idea is that you would generate one model based on this tool, then deploy this to all the similar kind of fans. So, for example, all of these, which are roughly about the same size, but then each of these pumps will have a slightly different vibrations and installation in general. So the model itself will adapt then in the final end use case. So there is basically a learning phase that you still do on the field, and then this way the model will get even better. All right, then the new thing that we have now introduced into our sensors just basically end of last year is this ISPU, which is Intelligent Sensor Processing Unit. And the idea is that you would run these kind of algorithm, for example, the previous NanoEdge AI with very low power then inside of the sensor. And then you can start to make different kind of even battery-powered applications, and just to start having the sensors monitoring many different kind of things. And when it's inside of the sensor, it can monitor the accelerometer or gyroscope data, but then also some external sensors, for example, the pressure sensor that could be connected to this one. And it's also possible to develop even any of your own algorithms just using a C language. So that's supported. Just to show you what it looks inside, that in the sensor components in general, we have this MEMS element. So this is actually the gyroscope portion, and this is the accelerometer portion. And then we have the ASIC, which is doing all the digital processing. And actually this core that I mentioned is located in here, in this same one. So this way we can also do the sensor component in very cost-efficient way, and also have the very low power consumption that's needed in these applications. Some more details of the component itself, that we are actually having a 32-bit RISC microcontroller inside. It's a RAM-based, so we have roughly 40K RAM for program and execution. So not to run very complex imaging processing algorithms, but especially just to check the accelerometer plus gyro data in low power. And to enable this, we have the floating point units, and then this kind of bi-NN convolution accelerator inside of the component to make these calculations faster. Also, we can wake up the 4 different interrupts a bit faster than traditional microcontrollers. And for this component, the target applications are indeed, for example, home alarms. With this type of device, you could see if the door is opening using accelerometer gyroscope data, robotics, see how the arm is moving, or then the condition monitoring that I mentioned earlier, and the NanoEdge AI algorithm that you saw, you can run it on this sensor component then directly. Another field could also be asset tracking in general, which could take benefit of this kind of low power. All right, we now come to the summary of the presentation. So we went through the different kind of sensors in the very beginning, just highlighting that again, that when making the measurements correctly in the very initial phase, you make the data logs correctly, and then you can make your AI algorithms correctly. And for this, we had this STWin.box development tool that then helps out to make these data logs in the very beginning. And then, as said, this way to moving from the traditional condition monitoring then to more fancier predictive maintenance to really understand when the devices are getting broken, and then which part of the equipment is getting broken. For example, if it's a motor or the bearing in it, and then the technicians can come with the right spare part right away to fix the problem with the help of sensors. All right, so the presentation is available. You can get it from this link in here, but you can just come to our booth with what we have with Anglia, and I'm also there, and I can show you some more details on this NanoEdge AI or then this STWin.box if you're interested to get still some more details. All right, I think it's now time for questions.
Thank you very much. Just curious, do you have a system, an exception-based surveillance system that sends you an alert when something goes out of the operating envelope. So whether it's an email or something, it just prompts you.
You mean to send an email or?
No.
Sorry.
So you have the trends, right? When it goes out of
Yes.
the operating window, operating envelope,
Yep.
do you have a system that would alert the operator, that will alert, the engineers that something is out of specification? So so the visual is clear, right? It's very clear. You look at it visually,
Yeah.
and but you have a system to send alerts.
System to send alarms was your question.
Yes.
Okay. So just as a background, so in ST we are doing the chips. So they are like the sensors, 2 times 2 millimeter of size, and then we do, for example, the microcontrollers. But we are not doing complete systems. That we offer these to our customers. But then what we do is then different kind of software packages to help out this. And for example, we do have a demonstrator using this type of board where we would actually make, for example, FFT to see the frequency, and then have a threshold that you can adjust. And then we just visualize that in the phone app over BLE, but it's a more like a example what could be then implemented by our end customers. We can also have a cloud connection from this app, and then it would be something that you would just trigger the alarm in the cloud itself. But as said, it would be more coming from our customers who put our components together, and we try to help them with our components and software solutions then especially. Okay, thank you.
Hi, yeah. I was just wondering if you're planning to add internet connectivity to your ST Winbox at any point.
Sorry, which type of connectivity?
Internet connectivity, like Wi-Fi?
Wi-Fi?
Yeah.
Okay. Yeah, so for the STM32s, there would be actually better specialists than me to discuss what we have available, but currently we have the Bluetooth, and then, for example, in this kit here, we are using external Wi-Fi module, but that's something which is available. And then we do have different kind of connectivity options from STM32s, and then also narrowband IoT chips just released from ST. So,
Okay.
but if you come to our Anglia booth, we have the specialist there who can help you, especially on this connectivity topic still more. Thank you.
Is the neural network and all of the AI stuff royalty-free, license-free?
That's a very good question. Thank you. So that NanoEdge AI, actually, if you run it inside of that sensor, it's a specific N variant then of the sensor. So there it's basically included in the chip price. So there is just a small additional cost to run the algorithm in there. Then if you run it on STM32, then to try out, it's for free, but then you need to get a production license, which is then the cost is based on also the amount of nodes that you are planning to use. So it's custom pricing then for the NanoEdge AI in that case. Very good question. Thank you.
Thanks.
Hi, thank you. I was wondering about when you mentioned about using Python in your NanoEdge Studio, AI Studio. Are you providing any sort of system to allow people to utilize other data science and data analysis methods in Python, such as pandas or other frameworks, including in your own software platform?
Okay, very good question again. On this case, we do offer, and the first task of this data log 2 was to offer the data logging capabilities and then visualization of the data, but we are adding more and more features to it, and I would need to check specifically with my software colleague, but I think we were working something especially with the pandas that you mentioned, that in a way that's something that we will be supporting also in the next releases.
Okay, thank you.
Thank you.
Question? Anyone has more question or?
Okay. Any more questions? Maybe no. So thank you very much for the big interest. It was